So we consider some application of this combinatorial nullstellensatz. There are several applications, but let's focus on the application in graph theory. So there are applications in additive combinatorics or many other areas, but let's focus on some application in graph theory. So before we consider the graph polynomial, and then we apply this combinatorial nullstellensatz to show that the certain polynomial is non-zero if and only if there is a proper coloring. So this combinatorial nullstellensatz could be applied to graph coloring problem. And for some context, it can be applied to the situation that we want to find certain subgraph. So assume that we want to find some regular subgraph. Alone, Friedland, Carlyle proved this. If P is prime, then every loopless multigraph with average degree greater than 2p minus 2 and maximum degree and most 2p minus 1 contains a p-regular subgraph. So here what we want to find is this subgraph which is regular. It doesn't have to be spanning subgraph, so it doesn't have to be vector, but some p-regular subgraph. Then what we can do is we can apply this combinatorial nullstellensatz. So we have to, so we want to find certain subgraph. And what combinatorial nullstellensatz give you is certain, values at each function, for each variable. So we want to connect this subgraph with the values on variables. And then we satisfy certain condition. And we want to find some polynomial where each of this value corresponds to subgraph. And then this condition of being p-regular is same as this f is not zero. So how do we do it? So subgraph is collection of edges. So let G be a multigraph with n vertices and m edges. And for each vertex, we let, say, gamma of b be the set of edges incident with b. So we have b, and there are several edge E1, E2, E3. Then this gamma of b consists of E1, E2, E3. So to make this connection, we define variables in this way. Define a variable x sub e for each edge e. And we define polynomial as following. So we take the all vertices, then we multiply this. What do we multiply is 1 minus summation of xe, where e is, edges incident with b. And we take a p minus 1 here, and we multiply all together, and then we subtract this. So there are certain purposes of how we take this. So you will see later, but this part is forbidding empty subgraph. So if you take no vertex and no edges, then that's vacuously p-regular subgraph. It has no vertex, so whatever vertex we take from this empty subgraph, it has a degree p vacuously. So we want to avoid that situation. That's the reason why here. So vaguely, if we let this variable to 1, then what we do is we choose this to include in H. H is the subgraph of G. And if this is 0, then we don't include. So this is 1 if and only if, every xe is 0. Otherwise, if one of them is 1, this is always 0. And then here you also see that by Fermat's Little theorem, this entire term is either 1 or 0. This is 0 if, they summed up to the number which is divisible by p. Otherwise, this is always 1 in, say, we are working on polynomial in, say, fp. So, over the field fp. So, this is always 1 or 0. And then we know exactly that this is 0 if this is divisible by p, otherwise this is 1. This is exactly the, once we give this way to construct the subgraph, this is exactly the degree of vertex p in H. And we can tell whether this is divisible by p or not. So that's how we come up with this polynomial. The degree of each of the n factors in the first term is p minus 1. And we know that the average degree in G is bigger than 2p minus 2. So what does it mean? It means that p minus 1n is strictly smaller than m. So number of edges is, average degree is same as 2m over n. So it's bigger than 2p minus 2. So we get this inequality. So the degree of the second term is m. So f has total degree m. So now we know that the coefficient of the term, this term in f is negative 1 to the m plus 1, so which is non-zero. So we can apply the nullstellensatz with being t sub e is 1 and each se is, say, 0, 1. And combinatorial nullstellensatz implies that for some y, fy is non-zero for some y, which is y1 to ym, is all of them are 0 or 1. And this choice selects h as if ye is 1, then e is in h, and ye is 0, then e is not in h. We know that this subgraph is non-trivial because if we plug in f0, everything is 0, then what do we get? This is 1, this is 1, so 1 minus 1 is 0, so this is 0. So this y is not all 0, so this is non-trivial subgraph. And this has at least one term which is 1, so if you plug in here, then this is 0. Hence the second term in the computation of fy is 0. And if for some vertex, if this value, which is the value of the term here, is non-zero modulo p for some v, then by Fermat's Little theorem, some factor of the first term is also 0. So if this is non-zero modulo p, that means this is 1 for some v. That means this entire thing is 0, so if you multiply, then everything is 0. Then first term is 0 and second term is 0, then every term is 0, so which contradicts that this is non-zero. So we conclude that h, in the graph h, the degree of each vertex is a multiple of p. And what do we know? We have one more condition, that the maximum degree is m-mod 2p minus 1. So any number which is divisible by p and smaller than 2p minus 1 it has to be 2p minus 1 because average degree is bigger than 2p minus 2. So only possible way is 2p minus 1. Then every non-isolated vertex of h has degree exactly p. As h is not trivial, so it contains at least one edge. This is the desired subgraph. So this is p regular subgraph. So by using this, we can prove the following. Before stating the problem or result, let me motivate it. We know that the graph with no cycle is a forest and having at most n-1 edges. And we know that the two regular graphs are exactly the disjoint union of cycle. So if we restate this, then we know that graphs with no two regular subgraphs are exactly the forest and having m most n minus 1 edges when n is the number of vertices. Then it's natural to ask, what if we increase this? What's the graph with no three regular subgraphs? Or, in general, what's the graph with no k regular subgraph? So for k is equal to, we know that two regular graphs are exactly disjoint union of cycle. So we know the complete structure, but there are, three regular graphs or four regular graphs. They are much more complicated. So characterizing, so here we have the complete characterization, but the complete characterization here is difficult. Then we can instead ask that how many edges can it have? So what's the maximum number of edges in such a graph? In other words, in here, if we have a graph with more than n edges, then it forces you to have two regular subgraphs. So what's the threshold that if you have more than that threshold of the number of edges, that enforces you to have a three regular subgraph or k regular subgraph? So Piber or Piber, I'm not sure which is the correct pronunciation. If we have an n vertex graph G and it has at least like some constant times n log n edges, then G contains a k regular subgraph. So meaning that the graphs with no k regular subgraph can have at most n log n times some constant many edges. On the other hand, for the lower bound on this, Piber, Rodel, Semoredi prove that there exists a graph with some constant times n log n edges, which contains no k regular subgraph. For any k at least 3. So it doesn't contain 3 regular subgraphs, and it doesn't contain 4 regular subgraphs, 5 regular subgraphs, and so on. So we will prove this Piber theorem by using this. We don't use combinatorial nullstellensatz anymore, but we use this to prove this. And for lower bound, it's we will not prove it, but I think this is a paper in 1995. So it's some probabilistic construction to show such a graph exists. So in the next video, we will prove this.